Hey there guys, and welcome back. So it has been a while for the stream animation program. As I've said numerous times on stream, in other streams, I have been working on this in my free time on break at work, just bits and pieces at a little bit of a time, and it is finally back in a stable state, so we will be going over all the changes that I made, as you can see here. Initial plan for the next update to the program was to get the pathfinding, which we're using A star for. That obviously was almost done, and then I decided that stuff had to change. So let's hop into VS Code, and I'll start going through changes I made. So, oh, looks like it lost, whoops, 1 second. I'll kick you back to GitHub, just a minute. I didn't realize that it had actually lost somehow my open in VS Code. Here we go. It had somehow lost everything. Yes, I trust myself. All right. So, place to start is the big and most important thing. So I was trying to not get too object oriented in this program, and I ended up backtracking on that. So we've added a good bit of object oriented code in here. We'll start out with the baseline, which is the coordinate system. Obviously, I also have a coordinate in here as a thing, as a class. It's just empty right now. I did not end up actually implementing that, but maybe sometime in the future we will. But the reason to implement a coordinate system as a class is so that everything is straightforward. So if you think back to the different, I guess, animation logics we had in the program, we had stuff where we said 4 axis and axes, and then we had to somehow get a hold of what those were. So now we just have a coordinate system, which a sprite or a engine should have attached to it, and we can just say sprite or engine dot coordinate system dot cs, something like that, in order to get access to whatever we need in order to actually use the coordinate system, in order to actually make use of the coordinate system. So you can see here, if you read this, we can have axes, or alternatively, we can use just directions. We can define a coordinate system with either of those. This aliases just has a list of other options for what those things can be called. And down here, as we go through here, if we do not provide directions, then we can generate those by taking the axes and just having lower and uppercase for the axes, for the positive and negative side of the axes. So, for example, lowercase x and uppercase X for the x-axis, and that would be the 2 directions on the x-axis. This obviously just converts everything from some value to the direction value that we actually need. This right here is a function just to take an offset. So remember, sometimes we don't always work with a direction, we might work with a coordinate. So this takes the offset, which would be, the difference between the coordinate and, well, an axis of the coordinate, a direction of the coordinate, and then determines whether that is, a positive direction or a negative direction. Determine offset is similar, so obviously we're offsetting -1 and +1 here instead, or 0 if it's equal, or if I'm sorry, 0 if it has not changed. So for example, how this works is if I have XYZ, okay, we'll have a direction, and it will normalize the direction, and then for axis in this dot axis, we iterate over the axis. So we have X, Y, and Z. If the direction is not axis and is not, or if axis not in direction not lower, then it's 0. If axis in direction, then it's -1, and otherwise it's +1. So that's how we sort out. So it might be 0, 0, +1, it might be -1, 0, 0. Just as it iterates over that, you can see how that works. Pretty simple. Let's see. Determine offset, again, operates very similar to, I believe we had this code somewhere else. It just goes over it determines the offsets for each of the axes, and then it actually, no, I don't think we did. I don't think we had this specific code before, but it uses this determine offset that we had before and then combines for each of the axes the value to get a net offset, diagonally, basically. For example, calculate offset. Okay, so calculate offset evidently is okay, yeah. So that is just between two. So the difference between this one and this one, I was trying to figure this out because it's been a while since I've written this. And as you can see, and this is something I found pretty interesting, as I was going back through the stream animations code, giving a quick look over, I realized I do not annotate this nearly as much as I do with Light-like. Light-like has annotations on every single line. This obviously is not. I believe the point of that was that with Light-like, I was doing code review and I was writing the code off stream, whereas with this, because I was writing the code on stream, basically I was going over all of it, and therefore all my annotations were, or wait, was I even writing this on stream? Yeah, I was. I think I started out writing this on stream. Regardless, the point is that the video was my annotations, which is why I did not annotate. I did not comment the code in here nearly as much. This mixed direction thing basically creates a diagonal for a coordinate system. So, for example, if we have an XY coordinate system, and we want and that would be a four-way, right? It would be up, down, left, right. If we wanted also up, right, down, right, up, left, down, left, if we wanted those coordinates as well, we can use this mix-in to just get all those different combinations. That's the point of this guy. And again, that is the single biggest change in this program. So let me hop on over to GitHub, get that up for myself so that I know where I'm going with this. So that was the big initial change that I made. And then I believe let me check utils right quick. Okay, now the next big change is going to be over in Sprites. It's definitely going to be over in Sprites. We'll stop by, what was it, engine.entities. Okay, I actually didn't do anything really with engine.entities, so we'll look at that really quick. So engine.entities got set up but never actually happened. So this is basically just behind the scenes code just to organize stuff. Nothing really to see here, as you can say. So we can assign IDs to sprites is all that happens here. We haven't actually added additional code here, and that's because I sidelined and went to other things. But as I was saying, oh right, systems. Systems is actually the next thing that comes after. So after coordinates, then we can have, once we have coordinates set up, I also implemented a systems object, which, for example, right here, system 2-dimensional. So in order to make sure everything is the same, we got the 2-dimensional 4-way, 2-dimensional 8-way here, which are coordinate systems for in the 2 dimensions. You can see XY here with aliases for up, right, down, left, etc., north, east, south. And then we create a sprite. And now when we pull the sprite 2D, so we used to have sprite 2D over in sprites. I renamed that to mobile sprite, and we now have sprite 2D here. And now the sprite 2D has the coordinate system tied to it. And that's the big major difference for over here. So the big major difference for over here is that if we had a 3D dimension, so if I had 3-dimensional as a system, we would have 3-dimensional as a coordinate system in here, and then we'd have Sprite 3D mobile sprite coordinate system 3-dimensional as the sprite available. Now there's also my plan was, and obviously we haven't gotten around to implementing it because it's not really necessary right now, to also add engines into here. That's definitely a possibility. So we'd have a 2D engine that might have special functionality for in the 2D, specific to 2D development. Or the other possibility is canvases. We might have canvases that are smarter about handling, for example, 3D. So that's another possibility. So moving on from that, I believe we're over to sprites next, would be the next big change. Let me glance at canvases really quick. Okay, yeah. No, canvases has a bunch of changes that will be affected by Sprite. So we will go to Sprite next. And Sprite was a major rehaul because, again, I decided to become more object-oriented to keep my things simple and my life easier. So first off, right at the very top of the file, you can see we have this animations and animation loop classes. So let me take a quick sip of water. Okay, so basically we had all these lists and objects in, or not objects, we're in Python now, so dictionaries, lists and dictionaries down here inside a Sprite for handling the animations. I decided to move all that out into its own thing, and that also made it easier to do stuff like, for example, here, pause and unpause. So in animations, we're going to have this dot animations, or this brackets animations, again, not self dot animations. I keep on saying this dot animations. Yeah, you understand me. I like obviously a whole bunch of JavaScript, so I'm going to be goofing up the exact terminology here. Fortunately, it has not been particularly goofing up my ability to write Python. Regardless, for each of those, so for example, in the mobile sprite, in what we used to call Sprite 2D, we had the cardinal directions, is what we were calling them at the time, and it would have a bunch of lists that ideally should work the same exact way for each list. And we would also have, in theory, also idle animations, which again should work the same exact way. In that we would cycle through the same exact way we cycled through the movement, and the same exact way we cycle through everything else. So since everything's identical, instead we just grab all those animations, and for each of those animation states, so again this would be idle, up, down, left, right, etc. We just turn it into an animation loop. We take all those frames and put them into an animation loop. The pause and unpause obviously is just a locking mechanism. A set animation is, one of those things, very simple. This dot current animation is animation. This dot animation, I guess, is not necessarily, this dot current animation is not necessarily obvious. So that would be the string key. So we would say set animation idle or set animation up. That's how we'd access this now in order to change what animation state our sprite is in. And then cycle is very simply, cycle until we get to the end of the animation, and then it will reset. All right, you can see it, wraps in both directions, etc., etc. If animation is paused, again, that's our locking mechanism, returns immediately. Current loop just returns the actual animation loop itself. Current frame returns the current frame from the current loop. And last frame tells you whether or not we're at the end of the animation cycle. So it's just some utility methods there. And then animation loop again. This code would have been used in several places. It's now all in one place. So we can just say animation loop.cycle to get to the next frame. And if the next frame is over, then it ends up being 0. This returns obviously the current index and the actual frame. And then current frame and is last frame is obviously pretty self-explanatory. And moving on. So down here you can see self.animation is animations with these guys. So we no longer have idle animations. This used to be idle animation or idle sprites or something like that, I believe, previously. Let me look at the GitHub. Yeah, idle animations. It is no longer that. It is now new an animations object itself. Let me see. I also evidently added this in. So if hitbox is a tuple and it's length 2, then it creates a rectangle hitbox with that of that size. So if you say hitboxes equals 3, 2, let's say, then it would make a 3x2 square hitbox and have that be the only hitbox. Just a simple little useful function in there. Is idle is now a property available to all sprites, and that just checks self.animations is idle. Very simple. Get image. Get image with hitboxes. I found this was useful for debugging. So now we can get the image with the hitboxes overlaid on the image, which is a very useful thing. Again, mostly for debugging, but what have you. We cut out in, let me just make sure I'm in the correct place right now, line 73. Line 73. Oh, that's right. Everything got shifted down. Everything got shifted down. So I guess it was at 144. 144. Which is where about we were at. So I deleted valid directions, determined directions, and determined offset, because then again, those are now part of sprite.coordinate system or engine.coordinate system, what have you. So that was a change. Paste hitboxes, obviously right here, is to actually get the hitboxes onto the image. Easy enough. I do color those in manually. So, or what was this? This wasn't actually colored manually, was it? No, okay, this is converting to this was a color conversion, is what this is. So as you can see, 255 is white, correct? Because zeros are black. So yeah, 255s get converted to reds in order to do the proper overlay, I believe was the reason for that. And next up will be stationary sprite. Yep. So this obviously changed a bit. Oh shoot! I just realized I'm going through this. I left that as, so that should be self.animations. Current index is not correct. You know what? I'll come back to that later. That's one thing that did not come up. We don't have a test word for that, evidently, because one of those things, the point of unit testing is that I just said, unit testing is good, and our sample outputs from the programs we wrote previously are good, so everything is working, and obviously that is not working. That would not be working if we had a for it. So that is the case. Regardless, cosmetic sprites also obviously, or was it cosmetic sprites? Let's look really quick. Yeah, so that used to have animations. It no longer does. Animations in theory is just in here in keywords. It used to have idle animations as a thing. Now it just says keywords to make my life easier. Hitboxes was obviously, get image right here was obviously updated to include with hitboxes. And then finally, the big one, 2D sprites is no longer 2D sprites, is now mobile sprite. And this is technically not correct, which moves around a coordinate system. There we go. So coordinate system, none, needs to be set ahead of time. And self.coordinate system can be set on initialization if necessary. Obviously, animations, get, etc. We go ahead and check that we have the directions for all our animations, and at the very end here, you can see animations equals animations. And as I said before, .cs, I had mentioned this just as a shorthand. So sprite.cs is a reference to sprite.coordinate system to make it easier to type. So in valid moves, I'm looking at... Okay, so we deleted valid directions, determine directions, and determine offsets on here, which is correct. And valid moves is new. Okay, so valid moves for direction in self.cs directions makes sense. So again, no matter what our coordinate system is, now we can just get all the possible directions the sprite can move. And with self at direction start, engine.move self, and if our location changed, then this is a valid direction. So for example, if we are on a single page canvas, which is one of our canvases up here, again, this engine, technically speaking, I know I have it set as engine.engine. That was only because I was eventually going to have inside of engines, as I mentioned before, canvases and whatnot predefined, but in the meantime, we can just use canvases as is, as our engine. So if we have the single page canvas, counts as an engine because you can actually move the sprite along it. Again, it has this move sprite function, which is what we need in order to use this function that we were just looking at, the valid moves function. So in that case, if we are in the top left corner and we try to go up one try to go up one or left one, okay, and we have a 2D sprite, our 2D sprite is going to get the is not going to be able to move up or left because the engine will stop it, because the single page canvas down here has the check bounds, self.check bounds, and it will return false, and therefore it will not actually move the sprite. And because it does not actually move the sprite's location is the same after the movement, which means that it cannot move, and therefore it will not yield direction. Direction will only be yielded if the sprite actually moved by the engine. So there we go. And that's a very simple update to what used to be valid directions to allow for, you know, different things, to allow for an engine to stop us from moving in directions we can't, etc. And this was important. This function was important to implement in this way for pathfinding, because also valid directions, I believe, yeah, just checked if the direction was in self.cardinals, which it does not include situations in which there's blocking terrain, for example. So obviously we need to also account for that. And yeah, that's basically all the changes. Obviously you can see we updated this, but this is still not technically correct, so whatever. Give me half a second. What? Okay, I'm done sneezing, I think. All right, back to the code. Hitboxes. Yeah. No actual changes in hitboxes. It's extremely minor. I guess that's not necessarily extremely minor, so I'll just touch on it really quick. Hitbox now accepts a sprite, so you can initialize a hitbox with a sprite. Previously, you created the hitbox, you gave it to the sprite, and the sprite registered itself on the hitbox. Now you can just initialize the hitbox with the sprite right away. So very minor change in terms of number of characters added to this code, but relatively important change. So what next? Covered all that. I think we are actually at that point. So I'm not going to go over all the unit test changes, okay? Because there was obviously quite, I mean, there were a bit. Not as many as I felt like there was, but we had a few adjustments to the unit test because we made all these changes over here in the code. Let's look at... Let's see. I'm just looking. I have some changes in canvas.gif, or canvas/gif, whichever. Do. Yeah, alright. So in GIF, over in GIF, the only real change is that we added this record hitboxes, and then later throughout this, we just throw that along so you can see sprites.get images with self.record hitboxes. So we have a bunch of little changes like that, where we just enabled the canvas to record, again, for debugging purposes, to print to the GIF the hitboxes. So that's all that is. And then on canvases itself, a lot of this had to be updated to reference sprite.cs instead of other things. So right here, sprite.cs, for example, sprite.cs, etc., etc., etc. Now that we're using coordinate systems instead of cardinals and whatnot. Cycle animations. Obviously, this got pared down to just sprite.animations.cycle. Very simple. Oh no, I take that back. We didn't actually have cycle animations. I believe what we actually had instead was we had the animation changed. I'm trying to find it in the code where we did it before. I'm not actually seeing it, so I'm blanking on how exactly we handled it before, but now we have this cycle animations function where it just very simply cycles the animations for the sprite. And and that is going to be it, with the exception of A star. So, A star. There are a lot of implementations of A star online. I just slapped this one together. I'm not going to say really quick, but you know, it's relatively straightforward algorithm. So for A star, what we're going to do is, you know what? Let me grab the camera. I don't use the camera too much on the programming streams, and therefore I got to clear some space here because I got a couple of things I was working on my desktop. But it's probably easiest to just draw this out. So, piece of paper, move my keys out of the way, and we will get to the camera. Here we go, light on. Let me check where the camera is at right now. Let's see. That button. Oh, camera's not plugged in yet. Ugh. Plugging the camera in then. You're going to hear Windows sounds now, probably. Alright. As soon as the camera's on, we'll take a look. Oh, wow. Okay. Because I unplugged the camera, it has decided that my exposure is redonkulous. My exposure and my white balance. So, half a second to fix that. Huh, this is funny. Alright, we're gonna keep that like that, and alright, there is that. Where is Funny thing is that looks pretty close to correct where I normally have it at, but, and I'm actually looking for a pen. There we go. But it looks like it might be glaring a little bit more than normal. Let me see what it looks like if I scribble here. Yeah, it looks a little bit more. So, let's see. Did not actually think about the fact that I might be using the camera. Otherwise, I had this set up. 128. That's probably all right there, right there. I don't think I got it quite where I normally have it, but actually, you know what? That helped. That helped a little bit. All right, there we go. Okay. Sorry for the delay, but here we are. So, whoops. In theory, with A star is very simple algorithm. We have a point that we're at. We have any number of other points that we can go to. And then we have a point that we need to get to. So if we're trying to get to the end point, T for target, from the start point, we're trying to get there in the least amount of time. It's basically what we're doing, generally speaking, with the A-star algorithm. Now, I've actually seen some other explanations where looking at the A-star algorithm, you can do other interesting things with it just based on how it works. But generally speaking, it's get from point A to point B in the shortest amount of time possible. So if this right here is, for example, 3 and 3, okay, to get from S to 1 and S to 2, they're both 3, then we're going to obviously check both of those, and we're going to see where we get to from both of those. So from here, I'm going to go ahead and draw out some more possibilities, some possible cells we can go into. Some nodes is what they normally call it. They normally call it nodes. So here's some more nodes, and we'll just call this 3, 4, and 5. So from this point, we have 2 nodes. Both of them are 3. We're going to start with 1 because that's the first one we came through. And then to get from 1 to 3, we might say that's 2. And 1 to 4, we might say that's 4, let's say. Okay. And then this one I'm going to go ahead and make 3. And this one I'll make 5. Cool. So A star, we're just going through. We have a list of nodes we can get to that we have not actually looked at yet. We started out with these 2. This is no longer in the list. 1 is no longer in the list because we already looked at 1 and we already looked at the other things it can get to. Now, in order to get to 3, we need to actually go 3 plus 2 for 5. So it costs 5 to get to 3, 7 to get to 4. We don't know about these 2 actually right here. I shouldn't have drawn these 2 just yet. Or 3 to get to 2. It's a lot cheaper to get to 2 from S than it is to get to 4 or 3. The only offset for that, which we can consider, is how far we think these are from T. So if we guess that this is, our guess we're going to say is maybe 6 from 3 to T and 5 from 4 to T. Those are our guesses right now. We may say that, and from 2 to T, our guess might be 7, okay? So if our guess from 2 to T is 7, plus the 3, well, we guess that's probably about 10 all the way, all around. Otherwise, we look at 3 to 4, and we can say, okay, 3 to 4 is 7, and then maybe 5, so that's 12. 5 and 6 is 11. So you know what? Maybe 3 is our best shot. We can use that as a heuristic. We can use these guesses as heuristics, or we can actually keep on exploring like this. We can also keep on exploring without the heuristics, because the fact of the matter is that we may actually get to the end on one of these routes, but if it's not the quickest route, then we're not interested in it, generally speaking, with A star. So because 3 is the lowest number, we'll go to 3. 3 will give us 3 and 5, so that's 6 to get to here, or 7 to get to here. We're going to obviously take the 6. So the 6, well, technically speaking, on the next iteration, we came here for 3, but this is 5 here. So we go 5 to here, we check 3, we find out that 3 is actually a dead end. You can't actually get to T from 3. So we've explored this, it has no possibilities, there's nothing left on this route on the stack. So remaining on the stack of cells we have not traveled to are 4 and 5. We can either spend 7 getting to 4 or 6 getting to 4. Obviously it's going to be the 6. So we're going to use that 6 instead. We'll ignore this one. This one just ends up getting overridden or ignored depending on how the algorithm got to it. Since we traveled this way first, that means that this actually was recorded first. We recorded that 1 to 4 was 4, and we know that that is now not the cheapest way to get there since we traveled to 2 first. So now 4 is the cheapest, 2 to 4 is the cheapest way to get to 4. We go to 4 because that's 6 instead of 8, and we find out that that can get to T with 5 as we expected. So now we have a route from S to T of 2, 4, and that has a total value of 11, but we don't know about 5. So we will come back, we'll check 5, and as it turns out, 5 is 7. Our heuristic was good. That is 12, so that is still not the cheapest method, and now we know for a fact that our cheapest route is to go start to 2, 2 to 4, and 4 to T. So that is a quick 5-second breakdown of the A-star route algorithm. And we'll now get back to code. Again, this is A-star is all over the internet. If you need additional resources, it's easy enough. We are going to look at the code I threw together for it. So we have heap queue in Python, which is a sortable queue. Heap queue will work off of if you provide heap queue a... well, let me actually just start going through the code. I take it back. I'm not going to talk about heap queue just yet. We'll see how it works as we go through the code. So the explore heap is list. The cache is the nodes that we've already gotten to, so we know the values of the nodes. The values it takes the cost right here that I have here to get to the nodes. Heuristic, the heuristic here, that is our guesses. Back that I had on the paper, I said, oh, I think this one's 5 because it's closest. It looks like this one's 6 because it might be a little closer than the other one. The other one's 7. So you need to provide it with a heuristic, which is just a function that says, give me your best guess on how close this is to our target. And that's just going to run on the start node. The start node is going to get its own heuristic, which is not necessarily relevant, but it's in here for completeness sake. Then we will create the start node, which has the heuristic cost. It has a cost of 0 because we're already there. That's where we're starting. Start is obviously the start coordinate, and none, which would be, as you can see here, previous. There are no previous nodes. So that's how we create our first node. Again, I didn't actually say this, but as you can see, node is a named tuple. So all that is just basically a data object tuple. So we can say node dot heuristic cost instead of node 0, node dot cost instead of 1, etc., etc., etc. It's just a simplicity thing. It really doesn't need to be a named tuple. It could just be a regular tuple. But for the sake of clarity, we are doing that. And then we put start onto the cache because it is a node that we have visited. We are caching the node. So while we have an explore heap, oh, I'm sorry, I skipped that line. Heap queue.heap push. So as you can see, we have the explore heap and we have the start node going into heap push. Heap push is going to take our list, put the start node in it, and it's going to, and this is the part I stop myself on, if you pass heap queue a tuple, it will look at the very first value in the tuple for where to sort this object into. Otherwise, heap queue, one of those things, it needs to have a way to figure out how to sort the stuff, and that's how that's going to work with tuples. I mean, I don't need to go any deeper into that because it's not relevant at this point. So it looks at the very first value in here, which is heuristic cost, and then it sorts the explore heap based on the heuristic cost. So if we have explore heap, which hopefully we do with the start node should be on the heap right here. If it's not, then something went horrifically wrong. Heap queue did not actually push it onto the heap. But we do have a heap, obviously, at this point. And current node is going to be heapq.pop explore heap. So heapq.pop, or heap pop, whatever, is going to get the lowest value object in the heap. Again, lowest value going off the very first value right here. And we check to see, first off, we'll assign that walrus operator right here, walrus operator, assign that to current node so that we can reference it. So while explore heap and the current node, the node that we just popped off the heap, is not our target. If it is our target, that means that we've actually made it to the target. We found the target. So we're groovy. And we found it with the lowest heuristic cost, which means that we should be on the shortest path. You'll recall, actually, let me just pop back over here to camera right quick. You'll recall that these numbers right here were only guesses, and we did not actually add this cost to T until we visited 4 right here. So once we visited 4 and once we visited 5, we added that heuristic cost to there. So back to code. If our heuristic cost is infinite, so this is just a way for our heuristic to say, and now you can't actually get to this node. Really what should happen is the adjacent function, which determines, we'll get to that down here. The adjacent function, which determines what cells you can travel to, really should not provide us with any nodes we can't actually travel to, but just in case, we got that. And then we get adjacent. That's right here, as stated. So we use this function with our current node to determine what nodes are adjacent to the current node. So we got new chord and move cost as the two things back from the adjacent. You recall that valid move, the function that we created or added 2 sprites over here, valid moves, returns, hold on, where was that? Derp, that was not the correct one. It wasn't valid moves, it was valid directions. Was it valid directions? I can actually figure this out really quick. Where's my A* sample? Oh, determine offset. Okay, that's what it was. Determine offset coordination. So over here in coordinates, determine offset coordinates. No, determine. What did I just read? Wow, this is a flop right here. Okay. Where did this end? Oh, okay, yeah. Sorry. So it is determine offset coordinate. So it's determine offset coordinate. There we go. So yes, I was correct there in that case. So back over here, 2 coordinates. So determine offset. The thing I missed here is that the A* sample provides the value as 1. That's right here. So this is the move cost to get to that in the A* sample. If we had hindering terrain, terrain that costs 2 or something like that, then that would have to be provided by the adjacent function. The engine itself, or the coordinate system itself rather, does not actually provide a cost to get to the adjacent square because it's not meant to handle that. The determine offset is obviously only supposed to return an offset relative to the, or I guess determine offset coordinate. is only supposed to return an offset relative to. It doesn't actually return the itself. So where did that go? Algorithms. Here we go. Keep open so that doesn't happen again. All right, so the first one is going to be the coordinate, as we saw, and then the move cost, which again is just going to be 1 in our A* example that we're going to look at in a minute. Cost to node will obviously be the current node.cost plus the move cost. So we got this move cost, and then this node that we popped off the heap, that cost gets added to the move cost, as we saw on the paper, to get the new cost to the node itself. So over on the paper, when we popped 1 up, this had a cost of 0 plus 3, so 1 had a 3. When we popped the 3 up, this had a cost of 3 plus 0, which is 3, and then the new cost of 2 to get there. So very simple. And then if the new coord is in the cache, if we've already visited this coordinate in our list before, we first check, well, the only thing we really do is check if the cost to the node is less than what we have recorded as the last time we got there. So when we visited here, when we got 1 to 4, we had that cost as 7. So right, the cache for that coordinate dot cost is 7, and then our new cost, which we just added, our cost to node, was 3 plus 3 for 6. So 6 is less than cached coordinate dot cost. Therefore, we update the cost and we say, okay, instead of using 1 as the coordinate as the node to get there, use 2 instead. So this becomes 2. Because current node again is the one that we popped off the heap, and the adjacent node is the node that we're caching. So at that point, regardless of whether or not it was cheaper, equal to, or more expensive to get to that node, since we've already looked at that node, we will just continue. We'll go to the next node that we found because we don't need to do anything else with that node. We've already explored that node, or at least put it onto our cache list. So we get the heuristic cost here, which is very straightforward. We call the heuristic with our new coordinate and our target. So how close is 4 to t, how close is 5 to t, etc. Add that to our actual cost, our cost that we know it is, and then create the node object, very simple, and push it onto the heap. We talked about this already, and onto the cache so that we know we'd already visited it. Now eventually we're going to either run out of objects or we're going to get to the target. So if we get to the target, if current node.coord is the target, now we have our root. So we start out our root from the current node, which is the target. We know this is a target, so this could just say target, right? One of those things. However you want to look at this, this could literally just say target right here. It doesn't necessarily matter. And then while current node equals current node.previous. So the targets, well, this is one reason, actually, I take it back. This is one reason why this can't be, no, it still could be, I take it back. Let me take back my take back. Yeah, so current node.previous, for example, in this situation, t, if we got to t via 4, if we got to t via 4, because that had cost 11, the previous node for t then would be 4 instead of 5 because that costs less. So previous node, yeah, I'm realizing actually that our doing this off heuristic cost is technically not correct, but that's really annoying. So this is what I get for doing this on break instead. I'm just gonna swap this right here. This is literally all we have to change. And at this point, we technically, the heuristic cost is useful for getting this to run quicker, but it's not actually necessary for the algorithm itself. It's an optimization. So if we want to explore all the nodes, technically speaking, we should do it the other way because we don't actually know until we find out that, for example, our root was S24, okay? T. That was our very first one. We got to T, and therefore our code would end there because we got to T. However, in the situation in which... How do I add this up so that it changes? Well, my point being is that this 7 right here is just a guess, all right? Which makes this 12. I guess if this was 5, we'd know that this heuristic value would then be 0, okay? In theory. So this would be an heuristic value of 3, 6, 11. And this would be... no, I guess it has to be lower. So this has to be something like 3. Again, I'm winging this off the top of my head. Maybe 2. So this would have to be a heuristic value. The heuristic value maybe here was misguessed. You know, let's say this was misguessed as 5. Okay, but it's actually 2. So we could end up going this direction thinking that this actual value was supposed to be 13 when it was supposed to be 11. Or supposed to be 10. Which is the point I was trying to get to. Which is why technically we should explore until we run out. But, however... again, the heuristic value is there as an optimizer if we wanted it. I was not actually planning on using it as an optimizer, but, you know, it is. So I just moved that around. So cost just got swapped there. One of those things. This actually then needs to be changed. So let me just change this really quick. Funny thing is that obviously the code is still going to work if there is only one root. And it's so the code will always work even if I have it this way. This way, again, will give you a slightly quicker result because we are not exploring all the nodes. We are only exploring nodes until we get to the get to the target. Yeah, just checking. That should fix it. So code still works even the way I had it before. It just ran a little bit quicker because we were guessing. In theory, it ran a little bit quicker. It may technically not run quicker depending on how bad our heuristic function is. But point being is that now this will explore every single node until the cheapest node is to go directly to target. So current node.previous, as I was saying, current node.previous gets added to, current node is now current node.previous, gets added to the list. And when we get all the way back to the start node, you will notice that the start node's previous is none. And therefore, current node will be equal to none, which is false. And therefore, we will not do the while statement. And at the end of that, you'll notice that we started out with the target and ended with the start node. Again, because the start node's previous is none. We then reverse it. That way it's going from the start node to the target node. There we go. All right. So that was A star. A little bumpy there because, again, I worked on this on break, which, you know, and that's break minus lunch. I didn't actually code while I was eating. But there we go. A little bit of, again, technically speaking, you could do this the other way with heuristics, but not necessarily the best way of doing it. So. Let's look at our A star samples. So I will uncomment this. KC. I have 2 sample. Oops. KU. There we go. I have 2 samples here for different A star solutions, and we will look at them. So first off, for all of these, we're going to have a single page canvas, 10 by 10. Step length is 1. And the background is just... did I make this light blue? Yeah, I made the background light blue. So here we have add listener, collision stop rule. So that is because we are going to put walls into here. You can see I have the wall image right here. We'll create the wall sprites further down for each of the maps. So we have the collision stop rule, so we do not run through walls. We have a character that will be running through the quote-unquote maze. I say quote-unquote because the first one is not so much a maze, but you'll get to see what happens. And then obviously we load up the sprite just the same exact way we do with all the other sprites. And now onto the map. So start is going to be 0, 9. On this one, start is different on the other one, but this is the bottom left-hand corner. So it's going to go from the bottom left-hand corner. The goal will be in the top right-hand corner. And then we will be placing 3 walls, I believe. Yeah, 3 walls. And these are stationary sprites with hitboxes 1, 1. Again, that 1, 1 was something I added to the sprite class so that we could initialize a single hitbox if we wanted to, and that makes sense for the sprite. So the sprite is a single pixel wide. It has a single pixel wide hitbox because it is a wall, and we are working in single pixel So as you can see here, character image is a 1x1 and it's red. And there we go. So we add these 3 walls at 6, 3, 7, 3, and 7, 4. And this makes a little kind of triangle shape on the map. Add the character in at start. I do it down here because obviously this setup has to take up place first to figure out where start is. Initialize the canvas. We should be very much familiar with this. And then we go to A star. So A star gets the character location. It has the goal. It has the heuristic, which here is linear distance. So let's go ahead and hop over there and look at that one. So let me just close some of this stuff up. AI heuristics, there they are. And distances. So I got a couple distances in here. We have square distance. So as you can see, that is sum of absolute differences across all axes between 2 points. And then we have the linear distance, which is, Pythagorean theorem, etc. So it makes yourself a triangle between 2 xy coordinates. So that's the one we're using right now. We're using the triangle, the hypotenuse between 2 coordinates. So moving on, that is our heuristic, how we determine how close we are to the target. Again, we're not so much going to use that at this point, but it's there. And then adjacent is, and again, it took me a second to remember how I set this up, but determine offset coordinate. So between the direction and start, and that direction is each direction in character.valid moves. So for our very first move, we are on the bottom left-hand corner, right? And we're on a single page canvas, which means that left and down are not valid moves. So our only valid moves are up and right. We pass up and right as the direction to determine offset coordinate, and that will give us up would be, we're at 0, 9 right now, right? Yeah, we're at 0, 9 right now. So up would be 0, 8 and right would be 1, 9. So those are the 2 values we're going to get back here, and each of those values get a move cost of 1. And then obviously every single time for each node, for each cell, for each tile that we visit, this will be called again for that tile, and we will determine new adjacent valid squares that we can move into, squares that are not not walls, squares that are not the edge of the maps. And for each of those valid squares, we will get the coordinate for that square using the determine offset coordinate, and we will continue in that manner. And at the end of A star, we have a character path, and all we got to do is move our character along that path. So for coordinate in character path, we create a new canvas frame. Again, this is a GIF, so we create a new character canvas frame, and then we paint. We get the offset here, obviously. Move the sprite to the offset based on the coordinate. That coordinate is the character path coordinate, and obviously we just cycle through all those frames until we're done, and obviously save it. Easy peasy. So let us go ahead and boot that up. Actually, I can come over here. I can do this over here too. So right click. Let me reveal in File Explorer. Okay, good. I got scared for a second that I might not have set up the... I guess I could have looked down here in the bottom right. I thought for a second I might not have set up the... the environment, the virtual environment. Minute to buy. Whoopsies. I typed the wrong thing. There we go. All right, so Python a star sample.py. There we go. That will create our sample map, and we can come up to here, or no, down here to map.gif. And here you can see our little red dot, our character runs to the corner. And as you can see, also, it avoided the, and I wish there was a way for me to, there we go. Yeah, you can see how it ducked up and around to go in there. It didn't just, let's come off again and look at it again. Yeah, so did you see that double move up? So instead of going right, so it was right here, and instead of going right into this square, because that's a wall, it went up one more and then went over. Now this obviously does not tell us how good it is really at finding the path, which is why we have the second example. That's just regular sample. Where is a star? There it is. So our second example is an actual map that I made, or maze rather I made. So I'll go ahead and uncomment this, comment that one out. There we go. And I have a whole bunch of walls set up in here. We put the walls in and then have the start and goal, etc., etc., etc. I'll go ahead and run this in the PowerShell. It is done. And we'll go ahead and look at this. So there we go. As you can see, this was the target for the record. I don't have any indicator on the map of where the target is, but it did go from its starting point, which is right here, all the way out and around, and took the most direct path possible to get to the end. Obviously, there are no actual other alternatives, so let me really quick just prove a point. And if I clear this box right here, that would be the I'm trying to figure out if there's any cheekier one that I could clear out. Yeah, okay, actually let me clear this box right here. So this is 0 1 2 3 wait 0 1 2 3 4 5 6 7. So 0 1 2 3. So 7 3. So let me clear out 7 3. Actually, you know what? Let's look at that one more time. So we know that the algorithm wants to go down here. We're going to, this would be quicker to go up. So if it goes up this time, then we know that it's taking the shorter route, right? So let's clear out 7 3. 7 3 is now dead. There we go. Save and rerun. And map. There's our hole right there. There's the target right there. And it now goes this way. So again, I don't know that that's necessarily definitive, you know, in your opinion. I don't know what you think. That is taking the shortest route, but it did not, at least at the very least, go in the same route it took before. As a proof of concept kind of deal. So, rerun this. There we go. And there you have it. Actually, the other one we could do is right here, I guess. Yeah, I don't know. There's probably a way. I could probably play with the walls a little bit and make a split so that one way is like, for example, 8 squares to it and the other way is 9 squares to it, just to get a better demonstration for it. But I think we can more or less prove that it is working at this point. So there we go. We now have our pathfinding algorithm. And the next thing that we'll be doing is adding some AI to our sprite. And the point was back over here, and actually, okay, I did not close it. Cool. Let me rerun sample.py. And it's going to take a second because, again, sample.py was actually a pretty big, and I believe I put those in. Yeah, there we go. And this is, you see the red? So the red was me showing hitboxes, what I was doing here. So again, with red being hitboxes, that's with the with hitboxes thing turned on. So the point here was that I was going to have things around the image for my sprite to run around to and do. So stuff like go and sit in front of the stream for a little bit. When this thing is done printing, and actually, if I click off of this right quick, you can see that I have this set up now to stop printing once it gets to the completion of a print. So then my character would have to come over, pull the print off, and then it would start printing again. That was the idea. So we were going to automate this so that we had some actual logic in the in the animation, so things are actually happening interestingly. And I, one of those things, add a little bit of randomization to it, so it's not the same animation every single time, and the character is constantly figuring out what it needs to do next, etc., etc., etc. Again, that is the next step that we will be pursuing, that we will be completing. So, anyway, that has been the hour that's taken to catch up on what we were doing, what I've gotten done with getting this code refactored and implementing A-Star. So anyway, we know where we're going, we know what we're doing now, etc., etc., etc. So, as always, if you have been watching, thank you. And I hope you have a great and wonderful day, afternoon, or evening, wherever you are in the world. And I'll catch you next time.